Okay, so let's continue from where we left off. Let's save this last file as 04 masters OceanFoam. Okay, so now we will drop here a dot network. Give this in black color and let's call this OceanFoam. Okay, and my dot nets are usually in black. So what I want is to dive inside and drop in a pop object. Name this guy foam. Okay, and let's create a pop solver. So that's the very basic .NET and a source, pop source. This is as exactly as dropping in a pop network. Voila. So what are we gonna do? So the first thing we're gonna do is, so I need to break this down to a bit more reasonable steps. Okay, so the first thing we want is to hook in our sources, right? So what I want to do is probably, okay, let's create some point groups for these sources. Let's create a group. Let's call this points from rocks. Let's call this waves, and that's it. Okay, so now what we can do is that because this is our main source, I'm gonna plug this guy here, I'm gonna plug this guy here, I'm gonna plug the source to here, I'm gonna plug the velocities here. Okay, and now I can go inside and we can create our sources. So what does that mean? So we're gonna have a pop. I'm gonna disconnect this now so I can rename it nicely. This guy is gonna be called src rocks, and it's gonna use points, and it's gonna use, I think we did the second one for the rocks, right? Yes. So let's give this a color, dark gray, and yeah, that's fine. And now I think I did enter some specific values: expectancy 6, life variance 4, interpolation by back using point velocity, and my constant birth rate is 1 million, but for testing purposes we're gonna go 0.1, so it's gonna shave off a 0. Okay, so but let's start like that. So the way I'm doing this is like this is because end of the day when we go to full caching we can just remove this section and it's gonna be a match, so we don't have to go back to see what was my value basically. Inherited value as it is. So that's the settings for rocks. So copy paste this guy. I'm gonna call src ww, which is this guy, and so that's the white water from the waves. I put 500,000 for this one, 500,000 times, let's go 0.1 for now, and 6x4 again, that's fine. So the source for this one is the first context, and again points, and everything else the same. So let's create a merge here, see with the same color, and now I believe I did randomize the, yeah, I guess we can use the same thing here. So we get a randomized values on the source points that intersects with the rocks as well. Okay, so we're gonna change the simulation start frame to 950, which is by default because that's when we created it. That's fine. So these are our sources. So you can put this in a network and call them all sources. We will need to expand this a little bit more later on, and because we want to put our boat as well there. But for now, that's fine. So now, obviously, we have some points. I'm gonna do that, and then what happens? So this is obviously not optimized because we have a lot of. Oops, I broke something. The camera changed. All the calculations changed. Let's undo because we are camera dependent, and I had the lock on. Come on. Okay, that's good. Now it should be okay. All right, let's unlock that. So this should be, yeah, that's fine, that's fine. What is my play speed, I wonder? Because no source is cached now. That's not so bad. Okay. Again, I guess this should be a bit slower. It's not so bad either. Okay, this would be faster than that. So my bottleneck is my VDB. So for now, let's go 2. Didn't really make that much difference. Okay, then we'll go 1. It's a bit more accurate. So let's dive in back in here. So if I press play now, obviously nothing is happening. If we turn these sources off, so this is definitely not V1, and also we are wasting a lot of computation power by putting points inside our collision mesh. So we need to get rid of that, and for that reason, which is here and here, we did create. Well, we do have a surface field, not for this from the waves, yeah, but let's drop in an object merge because we did create a surface field to be used as a collider in any simulation that we might need previously, and that is this guy here, this guy, and let's bring this guy in here, right? This, if you visualize that, should be there. Coming. Well, to be honest, this takes a while to load. That's a fairly heavy surface field, but we'll think about something. That's why pre-caching some of these sources is very important. Okay, let's go here. Let's go here. So we brought this guy here, which means that we can use the same method that we did for sampling to remove whatever points is in there. So I'm gonna do the same thing. I'm gonna call, where is the, okay, so that we can copy this guy literally. Let's copy this guy here. So it's gonna do the same thing, right? If I do that, and it just removes everything super fast. So that's before optimized. It should be super fast because this is a heavy cache, but it's loaded on the ones, and volume sampling is super fast. Do we want this for this? Not really, no, that's fine. That's already on the edge. Okay, so it's already optimized more. So now what we want to do is, the first thing we want to do is to advance these points with the velocity field that we made, and then we want to snap them to the surface. So how are we going to do that? We have pop advec by volumes, which we can use here. I'm going to give it a light blue color. And where is the velocity going? It's going to 0, 1, 2, 3. Okay, so I can change the third context, and my default I set 1.5, and just to improve the trace midpoint. So this is advection method. If you need these are not Houdini specific advection methods, you can read the details. It's just I believe this is just giving a bit nicer motion to it. So I'm just gonna ignore the mass for now, and so now if you press play, I will change my display to points so we can see the points better, and get rid of my none. If you play now, we should see some motion. Are we seeing any motion at all? We're not. So we need to investigate why nothing is moving, because they should have been moving. We have a velocity field on the fourth input, set the update force, however nothing is moving. Okay, so let's investigate. Which is this guy, and my force is up. Oh, there is a mismatch is due to resolution, I believe, but it's roughly in the correct place. No. Okay, let me check what's the problem here. We have a geo and an ocean surface, which is almost correct, and the difference is due to resolution difference, I believe. So if we change that to 0, that should sit better. It roughly does, but still should have worked. Okay, maybe it's coming from. Okay, let me pause the video while I'm trying to figure this out so we don't waste some time, and I'll be back very shortly. All right, it's working now. I guess I am pointing it straight into the, so we were using the fourth. I guess we did a mistake there. Instead, I'm now using parameter values, and I just locked this guy and dragged the velocity. Oh, this is for the source, my bad, sorry. So what I did is I selected, I switched the same thing for the sources as well. I selected node, I changed the SOP so I can fetch in directly from a node. I disconnected these wires and I dropped in this guy here. And now if I dive back inside and press play, you'll see what happens is that we have the points moving, but they have no concept of surface. So if something stays somehow outside, it will keep floating. It will, if it gets out of the influence of the velocity field, it will never get back on the surface. So that's not obviously what we want. Like you can see here, this is going to keep climbing. We don't have any gravity whatsoever, so that's not what we want. So how do we snap this onto the surface? Okay. We are going to snap them using our STF field and volume sampling. Credit goes to Entagma. They have done this some time ago, I believe, using I think it was an episode called packing radius or something packing. Well, let's now do that. So in order to do that, we're gonna create a pop wop. this goes under pop advec by volumes. And now we're going to dive inside, and let's call this foam setup. Let's give it a nice, we're gonna need some space for now. So now what we want is a volume gradient and then a volume sample. And what we want is that we want this SDF field, which is in the surface guy, to come in to our foam. So if you switch to input, we can now tell that we want in surface to be, so we can do like input 1 now swap, pin that, drag and drop in surface there, so this guy has a link here, and now which is this guy, so we can do that, we can do that. So now we are going to use this as a, I think we can, I just want to make sure that if we need anything else, but I don't think so. I think the surface is just enough. Output 2, oh yeah, that should be fine. Okay, so now I'm gonna unpin that. So we want the primitive number, using the primitive number, which is 0, which is fine. Again, it's the same thing. This is like just like the code we're using for sampling, and we can change from primitive number to primitive name, and we can type the name here, but we have only one volume coming there, so this is all fine. So we're gonna multiply the gradient by the sample position. So the sample pos needs to go to P. Therefore, okay, that's also correct. And what we need to do is to negate the result and add it to the current position of the particle, and this should now keep our particles on the surface of our geometry. Let's do that by putting it on so we can compare it to the geo, which we have is this guy. There's our low-res geo OceanFoam area, this guy. No, this one. Okay. So I'm going to, I guess, let's call this. You need to, because we are going to have other objects later here, like collision objects, everything. So just copy your top object and paste it here. So on the information that comes out from here are these particles. Drop in a temporary merge node just to verify that our snap to surface settings are working, and we are gonna run a little flipbook. I'm gonna pause the video now and we'll get back to it once we have a few frames. Okay, so this seems to be working. When we see the wave going down here, we don't have floating particles. That's good. Okay, so let's kill that flipbook and continue with the next step. So now one thing that I thought was lacking was that all those streaky particles that we see in like reference pictures that we see, you know, you always get these streaks behind big waves. So the way I thought that might work was to create new sources and advect some of those sources by the other particles, which are these ones, the master source, and the smaller ones. So we're going to use like we're going to create like effector particles which are going to be pulled towards these guys. So I'm going to create another pop source. And let's call this SRC streams. And I'm going to create another pop source. I'm going to name this SRC cells. And that's the basically idea I got from the new 17 solver. So let's select the streams. So we want these streams to be a lot less. So I just left it at 5,000 and I gave them a life variance of 4x4 and again change these values to interpolate by a source by back and using point velocity. And for source I am using the same source as my white water, so that is this guy. So I'm going to change that to points and here. But then I just want to create different random mass values for this. So I'm going to create a pop wrangle. And then I'm going to type at mass equals, and then I'm going to fit this. Well, actually it goes like this. I create a random value based on ID. And then I fit that into a different value. So it's like 0 and 1 is the random, right? But I never want it to be completely 0. So I go 0.1 to 1. Okay, so let's call this, I'm copying from that one, randomize mass SRC1, source 1. So what we need to do is that we're going to merge these guys here. This will come next, so I'm not going to plug this in now. I'm going to create another network box here, and I'm going to call it effectors. Okay. Now obviously effectors are not doing anything. We need to implement how this works, and for that to work we're going to use PC Open, which is very exciting. So if we dive inside foam setup, and we will try to optimize it as much as possible. So first we need to find, actually let's maybe do like a pop color here so we can see where our points are. So let's make these guys red and then make like these guys white, and let's remove the guides. Okay, so ultimately what we want to see is these white guys to be pulled towards these red guys. Okay. So anything around those areas will get pulled, all these white guys will get pulled toward these red guys while staying on the surface. So I kind of quite found that not so easy, but eventually I made it work. So what we need to do is first we get the and also we use the, so we need to use the because we created these guys here, right? So we create the streams and cells, so we're gonna have two separate workflows, one for the streams and one for the cells. So let's start by dropping a PC find radius, because we want to use random radius as well. And I want to create a random radius on these guys, which I need to check in my other scene as well, because I don't see it here now. Or did I? Live cell mass. Okay, well, guess we'll create it here. Okay, let me go back inside again. Oh no, because you're gonna expose that up. Okay, so let's go inside. File name goes to ourselves. Well, I think I need to update that as well. Yeah, so what I'm gonna do is actually I'm going to go outside and I'm gonna bring this up here because I want this to be myself. So which means I need to change the input of the volumes to be sampled from input 1 to input 2. Okay, so this is myself. So the myself goes as the file name, and now I want to create so this guy, I want this guy to work on the point group, which the name will come from here. So that will be the name src stream underscore src underscore streams, and I'll explain you what that means. So I need to post this here and copy that guy. Okay, so then my input is not a file but the first input, which is then now it's going to basically I want to use streams to be my group to look against my input. So it's like I'm saying, okay, all these points do a PC find radius using this group, which are the red ones. So this the str src streams is the red points. So it's gonna go point by point and it's gonna say, look around me, look around my current position only in these groups, and see if there are any points around me. Basically that's what it's gonna do. What I want to do is the radius scale. I'm gonna promote this guy and I'm gonna set that to 4. Is that what I named it? I changed the name. Rat scale, really? Okay, let's change the names, exact same thing, so it doesn't cause confusion after. I named it str scale here, and radius scale, rat scale. That's all fine, and it's by 4. Well, what's my 4 by default? So which is also here. That's fine. All right, let's go in here. So initially, what you want is first you want to see if this is working, and for this to work, we can do len. So array length. So what this does, if I do a middle mouse here, it's gonna result. This is gonna turn a value. So I can do like a bind export test. And if I go to geo here, now I should have a test attribute, and now this is returning me some values, which is the length of the array. So like, how many points did I find? Okay, so it seems to be working. That's good. So now what we want is that we want to loop over all the found results, right? So we don't want to run our additional operations on the points that are not found and just ditch the values, but we just want to like, okay, you know, run over this, run over this, run over this point, this point, this point, this point, because you're within the range of 4. So in order to do that, we're gonna drop in a for loop, and first input, not for loop, sorry, it's the one with the array. I think not this one, for each. Oop. Yes. So because it's an array, so array goes to array. Let's pull, maybe bring these guys a bit further down, create some space. And let's bring this guy a little bit back. And this goes here. So now what I want to do is that I want to iterate over this point and then create a vector from all these resulting points towards this guy. Okay, so this guy, I'm gonna say, okay, I'm gonna create a normal against my target point, and then they're gonna draw some normals, which we're gonna do now. So how do I do that? So I want to get the position of the each found node by putting in a get attribute node, and I'm gonna connect element out to I1, and then my I2. Well, it's my other network is quite hectic here, so because I need to go exactly the same. No, my I2 is alone, sorry, but my A default should be, I think, my position. I need to double check that, but I'm pretty certain it is, but it's not my current position, it's my manipulated position. Remember, we moved the points. Yeah, same applies here, because we are manipulating the points, so we are moving the points to the surface, so we need the result of this, and then after we move them we need to do the math, so in the correct position. If we connect the P to the input P here, it will be before we move the particles to the surface, so that will not work. Okay, and now I want to subtract the position of, but here I need to say P, and then I need to change the input to first input. Okay, so it's gonna get the position of the found object into my loop, and then check against the position, and then we're gonna subtract that from, again, our adjusted position. So here, and now this is gonna come out as I'm gonna do one here. No, I want in one. First one I want to call distance, my first output. Second output I want to name it vector direction. So this is my vector direction. This goes in here. Now I want to measure distance as well, because I want to affect, because I'm gonna create a force and I want it to have a fall off based on distance. So I'm gonna create a distance here, and my P1 is my manipulated position, and my the result, the position of the point in the array that came out from the PC open. And then what I want is I want to fit this range. I want to normalize this. So this is the value. So my source max is actually my defined radius now. Okay, and this is my distance in. So now I think if we plug this as a color, we should see something happening. Okay, let me play with this a little bit so we can get a better idea. Yeah, so you can see some gradients here. So maybe 4 is too much. So I think if we go now here and drop this value to something smaller. Okay, so maybe more. So you see so we start seeing some gradients. Okay, how can we, because it's the red, so there should be the red ones in the middle basically. If we cut this, so there should be more advection around those areas based on the density of the red areas. Okay, the other thing we can do is to draw the direction. So if I bind export this guy and call it force D as a vector, and then I go in my visualization and add one here, marker force D, and this is not a text, this is a vector trail, and that should draw us our direction. Okay, let's change that to this is fixed color, vector values maybe, or vector directions. Okay. If we normalize, should we normalize them? No. Okay, so you'll see like there's a radial pattern, and this means that our force is probably working fine. Like all these points will aim for those red points, to the nearest one at least. Okay, so I don't need this anymore. Now, what I am gonna do next is to add this as a force. So what I can do is that I can say vector direction is actually now a force. So there's a lot more steps to do it yet, but we're just gonna play now to see what's gonna happen. It's a bit difficult to see these big points. Where is our camera? It's here, right? So maybe we'll be able to see it here. Okay, I guess if you focus on this area, I'm gonna make these points bigger. It's not a single direction anymore. It's like some points are going for some other points. Obviously we need to balance these values out, and that's what we're gonna do here. So let's dive back inside, and now what I did is that I am going to export some of these attributes in case I need them. So I'm gonna put a bind export here, and the direction, the distance out becomes my fall off attribute, which I call strength fall off. And then I put a multiply here because I want to be able to manipulate this value by hand. What I did then is I brought in my mass, and I brought in my vector direction, which then I multiplied by my fall off, which then I multiplied by my mass, and finally an override if needed, which I called str force. And by default I changed that to -2 because I wanted to pull everything back. And the output of this is now going to go into force. And now we can put some nice colorful boxes around this. So this whole section is going to be moving up here, I'm gonna call it streams force. This is this guy is gonna have its own window. I made it this pink. No, it's not pink. This pink because it's pretty. Let's make this guy a little bigger. And I gave it a name just to be clear. Finds streams and creates efforts towards them. Creates efforts towards them. Okay, and then this guy is our loop, obviously. And finally, I'm going to create. Let's bind export. So this is our calculated force in the end. So that's strf. That's what I call it as a vector. So this is our final force value. We may or may not need those, but stream force, I'll keep it for now. And let's put these guys in another network. And this is our final stream force. And let's give it another color. Okay, so this is our first loop. Now the other loop is going to be to create a cellular structure, but first we need to see if this is working. And in order to see that if it's working is that we're gonna crank that value up, and then we're gonna change that value up to see if it's in the good range. So in order for this to work, I'm gonna set the same values for now, and maybe increase my source numbers a little bit, maybe go 5. So we have some more, and we can do the same for this guy. And I didn't actually change this one, so this is supposed to be parameter, and we bring in this guy here. Okay, so it's there. Okay, so we still don't have any collisions or anything. What we can do is that I can disable these, press play. Okay, I guess the best way is, before we do anything, we make 2 play blasts. I'm gonna put a switch here. And so input 1 will be the force bypass, and input 2 will be the final value. So if we switch, and let's call this, not here, enable streams. Let's call this enable streams, and that's a toggle. Enable streams. Okay, so if I turn this on, we should see a difference. If I leave it like this, we should see just general advection. So in order to do that, I'm gonna make 2 play blasts, so we can see if it makes any difference. And I think that's the best way to measure it. And so we start at this guy. I'm gonna pause the video. Okay, so I simulated to 1031. So that's what we get with the toggle off. So let's click on this guy, so we can have it accessible from the sequence list. Let's turn on the toggle, so which would now actually switch the force to use what we did here. And I'm gonna do another play blast, and I'm gonna pause the video, and then we'll get back once we have enough frames. Okay, so now I paused it with the toggle on. So now we can see that there is a different, actually let me put this in layout. Where is that? Zoom layout, 2 columns. And then I'm gonna switch this guy to the old one. So you can see that our system is working. Me go and set the last frame to 1030. So this is the without any streams. This is with streams. So our setup is working, although it's not with the desirable numbers. I think that our streams are we have too many streams. So I guess we will eventually end up getting less points. So we have less streams. And then we're gonna put some because now there's no spatial awareness between the other points. The force is just gonna keep them pushing until they converge to a single place. So we're gonna force them to use keep some kind of distance in between as well. And let's give this guy a gray color. Let's also make a little network box here. Let's call this foam accumulation. Okay, so now what we can do next is the cellular structure. Luckily it's a very similar approach, so we just have to copy this entire network and paste it up here. But now we need to bring in the source cells, which is gonna be let me see here. So this is gonna have a lot less random mass to it. So it's from 0.8 to 1. So what this will do is that because we have we are multiplying our mass with our force, so this is going to give a more broad, more narrow, more, how to put it, so because in the streams particles we had a very big variation of mass, so the final output of the velocities were different, but these guys have a very narrow mass difference, so the output of their forces will be with less random values. So to do that, now we need to give this guy a different name. So now this is the streams force, this is our cell force now, so we're gonna go cell force. Let's change the name to cell scale. And this can be called scale 2, and this can be cell scale, and default this one now. And now this is going to get stream. Instead of streams, we're going to use the stream SRC cells, and our radius is gonna be, where did I put that? Well, there's one thing I think we missed. Let's do that as well. We defined the radius, which we forgot here, so defaulted. And our radius is, where does it come from? Sorry, my bad. This is a constant, and it actually goes to our source max. I made a mistake. So remember, we plugged that to rad scale. Let's plug it to our radius here, and our radius value by default is a constant that is 0.5. So I'm gonna go here, and I'm gonna go what was the name? Just radius, search radius. Okay, so the search radius will be 0.5, and this is because this is a multiplier. This is the actual radius value. So we are doing the cells now. Finds, let's name this so it's clear. Finds cells and creates forces towards them. And it basically does the same thing. I just want to make sure that it is connected to the correct place. It's using this str cells, which is this guy, so which means that we need to merge this dude here, and which means that I need to make sure that they are using the same correct values as SRC cells. So it's using the points, 5,000 points, but it's leaving a bit too long, so it needs to be 4 by 2. It's positive, back, use the point velocity. So if things move too fast, the points will be created in a good place. Source needs to be points, and it's the source points, so we're using this guy, which is this guy. So copy this and go into the cells, points, use not object parameter. Okay, so now we have this guy as well. Bird, I think 5,000 is too much. I think it was 500. Okay, that's what we want. Okay. And now I think so we should have the str cells. Okay, so we're good. So let's go back in here. Just going to make sure that everything else is same, which should be the same. This is the cells. We're doing the exact same math. Okay. Yeah, except we're gonna change the names now. So this is a cell fall off. Cell force. Cell force. And this guy is now named. Wait, it's not this one. It's this one. Yeah, so this guy is now called cell fall off, and this one is called cell force instead of strength force. So if I plug this guy now in to here, it should show me only the cell force that is being applied. I just want to make sure that we have the good values, which is the 0.5 and cell scale. Yeah, okay, so there's one more thing to do, is that the cell scale, no, that's fine. So we need to go outside, and let's start with the values that I've already found to be good. So cell force is the one we're missing here, which we will create, and cell scale is 1. That's fine. It's just that there was a multiplier that we had here. It needs a different name, which is cell force. Yeah, when you duplicate things, you need to be very careful. And our cell force is also -2. And now if radius scale, wait, radius scale is not -2. Yeah, there's a little complication here. Cell force is, where's my cell force? Didn't change the name. Let's dive back inside. str force, cell force. Ah, there it is. Okay. We need to put this in order. So let's go to parameter interface. It's under the, let's close all this. So I want this to be on top. Then I want stream force also here. Apply. Okay. Enable streams, we can put that on top. This is for testing anyway. I'm gonna get rid of that. And so then I want my radius scale and cell scale. And I have this search radius. I don't accept. Okay, so this guy I'm not so sure. Oh yeah, no, that's fine. So cell force is -2. Radius scale is 4. That's what we left off. Cell scale is 1. Okay, and now I think. Okay, so we're still testing the output of our cell force this time. So what we can do is that we click on this guy, so we preserve this play blast as well. And now I'm going to do another play blast to see what the cell force is doing. I will get back once it's some frames. Okay, so this is working as well, although I think you can see that our cell scale is too big. You can see that they're like really big, and we don't want such big cells, and we will manipulate the data further, but it seems to create much nicer streams, so we just have to find a nice balance for this to work together. Okay, let me rewind to the first frame. The last thing we need to do before I finish this lesson is to use these two forces by mixing them. So how do we do that? So I'm going to create a divide force, the divide operator, and we're gonna get the age as the first input. I think we do have, okay, let me just check something. What happens if I bind export in age? Do we have, because this always confuses me with Houdini. Always. It should be a normalized age, isn't it? An age, maybe it's bigger. Yeah, it's because it's preserved somehow, so this doesn't work. Okay, you know what? I'm just gonna make my own because it's just a small operation. It's no biggie. So the first input is age. Divided by life will give you a normalized age. So we want to use this as a mix, a bias. So then what I do is that this is the normalized age, right? So I'm gonna put a ramp here so I can shift the weight if I need, and I'll call this transition range. And then what I want is that I want to drop in a mix, and my first input is my streams, my second input is my cell force, and my bias is the output of this guy, and then this guy goes as force. And we don't need that anymore. That was only for testing. So now, basically, based on how old the particle is, the force will shift from one force to the next. And I think the other thing we can probably do is this needs to go. We forgot that as well. Need to connect the radius to source max, because this creates a normalized fall off. And this is a cell scale multiplier, this is a str scale multiplier, and this radius is same for both PC opens, but what this? So here's the thing: PC find radius is actually a bit more expensive to use than PC find, because this guy, I believe, accepts variable p scale. I think. Let's read, because I'm not entirely sure also. Okay, well, I guess we can get back to that. This is not really, well, I don't really get a slowdown, to be honest. Gives a bit more control. But I'm going to call this a different here. I'm going to call this str radius. So stream radius. And let's just do it like that. And I'm going to copy this. Plug this guy here. And call this cell radius to have a more granular level of control. Cell radius, cell radius, cell radius, because I don't want cells to be that big. And then cell scale. So there's a cell scale, radius scale. So this radius scale, we can rename that. I think there's a cell scale. Where's the rat scale? So this is str scale. Okay, here. Let's name these also, so it's understandable. Okay, I think now it's a bit more clean. It's very important to get these networks, spend some time on these networks, because it gets very, very busy very easy, and after it becomes a nightmare, especially if you're working with other people on these projects. Okay, so then this guy is here, except though str radius, cell radius is now here. Okay, this is the wrong connection. Cell radius becomes its own source max for the fall off, so that gives us a normalized distance. And this guy goes here, this guy goes here, almost like this, like this, like this. Okay, and I'm gonna pull this down a little bit. Okay, I think our first part is done. So the next thing I'm gonna do is to drop in a pop interact, because this has the ability to push the points a bit further apart from itself. And here's the value I'm using, really small values, and this is just gonna keep, so the points basically never just hop on top of each other. Okay, let's just move this guy up. You come here. Now maybe we can run the final test before we finish this video. Let me just save this, because it's been a while. I guess I'm gonna change the camera angle, because we have quite many. Now we can actually, let's just get a better angle. Maybe increase these values a bit. Let's give it a 1. That's fine. This is not gonna change. And what I want to change was to change the cell scale. Search radius, right? Cell str radius, cell scale, with the cell radius here. Okay, so let me just go move that guy up to its proper place. Cell radius goes up to here. Oh, so this, we don't want this to be a vector. We want this to be a curve. Where are you? Change it to spline ramp and possibly get a similar curve like I did. You guys can select. So I like to work B spline, it's just, I think, more cooler. It gives more smooth values. So you can select the node and then just switch to B spline. B spline is going to create this spline curve. So that's kind of what I did. My values are like this, but what I want, I think, is cell radius to be smaller. So this is the search distance, and this is its multiplier radius. So str radius, so let's go to 2 as well. Cell scale was 1, radius scale is 4. I think we can go 3 as well. We don't want so much little streaks. Okay, let's do the final play blast, and then we'll move to the next video. I'll pause it now and get back to you with some frames out. Okay, so this is still going. So what we made is working. I think we are a bit over the top with the force amount we're applying. So I think we can dial it down. But this popnet has not finished yet. We still have to bring in our collision shapes and add a bit more work on the values themselves. But I'm gonna save this and I'm gonna split the video into another video because this is already over an hour. All right, thanks for watching.